So don't worry, be happy. That was the song played before the class, before the lecture. I hope you guys don't be worried, be happy. Although I know it's close to our finals week, but don't worry, be happy. I mean, well, on the positive side, no matter how you perform in the finals week, the days will go by and it will go over, right? It will end. And sometimes I like the quarter system in a way is that no matter how suffering you are, a quarter is just 10 weeks. But if you are in a semester systems, then it will be 15 weeks. But today we are going to, but if you really want to, okay, so one thing, right? Don't worry, be happy. And if you really don't want to be worried about your finals week, then the lecture today is very important. And in fact, every lecture is very important. But I do want to let you know that the lecture today is probably one of the most most useful lecture for the rest of your career in terms of the content that we are going to teach today. So today we are going to talk about multi-threaded architectures and programming on multi-threaded architectures. But before we start, it's always good to remind you where we are coming from. So we said now every processor that we are using is a superscalar processor with real order buffer. And the reason why we want to have a superscalar processor is because right now every processor has many functional units. And if you want to fully utilize these functional units, if you just execute your instructions based on the program counter order or say the compiler's order, there's no way that we can fully utilize them. The approach that we take is that, okay, we have superscalar processor plus auto order issue, which in a way that we are able to issue multiple instructions at the same time to multiple different functional units and allow them to be executed regardless of their original program order, as long as the instruction has all its input ready. However, to guarantee the correctness of your program, we still need to make sure that all these instructions are completed in their original order. So that's why we have the reorder buffer. And with reorder buffer, if there is any exception occurs or any branch misprediction occurs, we are able to flush those architectural states that are not supposed to change. So that was where we are. However, even with superscalar processor, if you look at code like this, like a linked list code, then the instruction level parallelism, meaning that the concurrent instructions that we can issue in a pipeline or say we can execute in a pipeline is still low because of data dependencies. And I can give you another demo regarding how low the instruction level parallelism is in your code. So if you are familiar with the matrix multiplication code that I have been demoing in the past, right? If I'm running a matrix multiplication on 2K by 2K and use the tool perf, and let's see how low the IPC it is for now. And the program takes a while, so we will go back to that later. So, but for now, let's keep going on. So because the IPC instruction level parallelism is really low, so turns out that we have no way to fully utilize our functional units for a single thread. So that's why we start to explore other options. For example, an option that we explored in the last lecture is simultaneous multi-threading. The basic idea of simultaneous multi-threading is that because we are not able to get sufficient amount of instructions to fill in the functional units within a single pipeline. So what if we duplicate part of the hardware to present an illusion that the processor is capable of executing multiple programs or multiple processes or multiple threads at the same time? And to achieve this, we need to have two sets of program counter, two sets of register renaming table. Your instruction queue must be partitioned among, or say reorder buffer must be partitioned among these two different process, this multiple different processes, multiple different threads, to make sure that you are still able to maintain them in the correct order. So with that, we are able, whenever we are able to get instructions from different processes to fill in our pipeline. So you can imagine simultaneous multi-threading is able to improve the throughput of your execution. And whenever you have a branch misprediction, or you have a branch, it's possible that we can schedule instructions from other threads to fill in the slots when we are still making decisions on the real branch outcome. So in this way, if we have a branch misprediction, the penalty is lower. And and it also helps us to increase the hardware utilization, because that's the whole purpose. We are going to fill the pipeline with other instructions from other threads. And the hardware design is the complexity of additional hardware design comparing with superscalar processor is minimal, in a way that you only need to duplicate PC and register files and potentially roll the buffers. And it's very popular in modern processors now, like Intel's hyper-threading technology or AMD's latest Ryzen processors. They all have simultaneous multi-threaded inside. So if you look at the, if you look at the, yeah, so that's the current state of the art. And if you look at the design of modern processors, right, the pipeline of modern processor, although I make this papers optional, but you should have at least take a look at this paper. So in the syllabus, we also talk about the pipeline of Intel Skylake processor, and given the knowledge you have, it's probably not too difficult for you to figure out what's going on in this pipeline diagram of Intel's Skylake. So to begin with, right, let's start with this. So this is instruction cache. So Intel Skylake processor has a 32K L1 instruction cache. And the instruction cache, it will contain instructions, and that will be later fitted into the decode stage in the Intel pipeline. And what instruction to fetch is actually coming from the BPU, branch prediction unit, in Intel Skylake processor. So this is like the branch predictor of Intel Skylake processor. And the decoded instruction, so the decode here means that I am decoding the x86 instruction into, they say there here is a decoded iCache. So what's a decoded iCache? So Intel, so all the Intel processor, or say AMD processor right now, they have a front end instruction support for x86, but internally they are run RISC like micro ops. So after you decoded this into these instructions, they will be put into the instruction decode queue, and this instruction decode queue will be later on being allocated, renamed, retired. So this, you will imagine this is a combined renamed instruction queue with all the buffer in Intel processor. So after you rename this micro ops, which is RISC-like, the scheduler will check all the data dependencies of instructions in the instruction queue. And then if the instruction is ready to execute, it will be issued to one of the following pipelines. So as you can see for Intel processor, there is a pipeline for integer vector operations. And actually there are 4. And there are also 2 of the load pipeline, and there are 4 for store. And those data access pipeline, they will be connected to the L1 data cache. And there is also an L2 unified cache that's combined for instruction and data in Intel processors. And following, there will be an L3 cache that's shared among all processors in an Intel processor. So that's the high level architecture of Intel's Skylake pipeline. And as you can see, this is a super scalar processor, given we have so many integer ALUs or floating point ALUs that we have. Okay, so that's Intel Skylake, and the same, and as you can see, this is a 4-issue integer pipeline, 4-issue memory pipeline. So it's a multi-issue superscalar pipeline. And for AMD processor, it's also the same, right? They still have the branch predictor, and they have the instruction cache, 64 kilobyte 4-way. And with the instruction, so the instruction cache is like the instruction fetch unit. And then the decode stage, which again decodes the x86 instruction into micro ops. Micro ops is the internal RISC instruction used by x86 x86 processors. And Intel and AMD, they have their own private RISC or say micro op that they never tell you what they looks like. And for the decode stage, AMD says that we are able to decode 4 instructions per cycle. So 4 x86 instructions will be decoded per cycle, but each x86 instruction will be further decoded into multiple micro ops. And then in each cycle, they can dispatch at most 6 operations, micro ops. And these 6 operations could either go to one of the 2 units. One part is the integer units. And for the integer units, there will be integer rename. So they will rename their architectural registers on the integer part and into the physical register. And floating point, they also have a renaming unit that renames their floating point architectural register to the physical floating point registers. And then there will be scheduler, try to schedule their operations into one of the 6 LUs for the integer, or one of the 4 for the floating point. And if there is anything that needs to access data, 2 of the integer pipeline is actually the address generation unit. You can consider this is an address queue, address resolution in a pipeline that we just learned before. And they will be further dispatched into the low store queues and access the data cache. And it also has a 32K 8-way data cache, but a larger combined unified L2 cache in the case for AMD. So as you can see right now, after you learn, we taught you in a class, you are able to look at their pipeline diagram and understand what's going on in a paper, in this processors. However, now so this is just a core in a processor. If you look at the whole Intel processor, it actually looks like this. So the core that you just see is actually one of this. So the Intel Skylake processor, what we just explained is just this square with L2 cache. However, beyond this core, there are still shared L3 cache and a lot of logic here for the IO, the memory controllers. So one big takeaway here is that what we have just learned so far is one of the single core. However, the real processor are actually all looks like this, is a multi-core processor, and each core may have an SMT capability. So for example, like the Intel hyper-threading processor, they have the 2-way support for SMT, meaning that it can present a core as 2 cores to the operating system, but 2 of the thread or 2 of the processes, they will be scheduled into the same core. And a single Intel processor actually have 4 to 8 cores or even more cores on their chip. So these processors that you are seeing, and the same thing for AMD processors. For AMD Ryzen processor, if you look at their design, it's also like this. And this is like an 8-core Ryzen 7 processor. And as you can see from here, they have 8 different cores, and they build a cluster So each core still have its own private L2 cache, and there is a shared L3 cache for each 4 of their cores. So you can see right now, almost every processor looks like this. So why? Why we design processor like this? So today we are going to talk about the case for chip multiprocessor. We are going to talk about programming in multi-threaded architectures. So I think it's time to look at our profiling result for the IOP case. So if you just look at the perf result for the matrix multiplication, you can see for the program, we can only execute 0.79 instructions per cycle. We can only get this level of instruction level parallelism. So it's pretty low, even though I have a program. Most of the time, my program won't be able to fully utilize my processor, like the case that I just showed you. And it's a very common case that if you look at this paper, which we are going to discuss, there's a table here. It tells you that most of the program, the instruction per cycles, or say the instruction level parallelism, is about like for this column, everyone is smaller than 1, and for this column, everyone is smaller than 2.2. Right. So what it tells you is that even though I have a 6-issue superscalar processor, and remember how many issues do we have in the AMD Ryzen processor, and it's actually 6 issue, right? So even though you have an AMD Ryzen processor, if your program looks like this, right, and there is no way that you can fully utilize the processor anyway, even though you have simultaneous multi-threading, saying that I can put 2 programs together, it at most just double the instruction level parallelism, saying like from 2.3 to 4.6, right? So that's not you are never able to fully utilize your 6-issue processor in this way. So it doesn't really make sense that you build super wide issue processors. And another issue is that if I want to build super wide issue processor, first of all, you need to have an instruction queue. And the issue logic needs to be really large. And the other thing is that if you look at the wires here, it's going to be really large. So the area is going to be, you are going to spend a lot of area in building a processor. So here comes the case for single chip multiprocessor, which is the general architecture that you are seeing for all the processors that you can purchase right now. Even your mobile phone is using a single chip multiprocessor architecture. So what's the motivation behind chip multiprocessor is that we just mentioned that if we have a 6-way simultaneous superscalar processor, means that we have a 6-issue processor. And it takes 20 in the era that the paper was developed, it takes 21 millimeters square to build a 6-way superscalar processor with 3 integer ALUs, 3 floating point ALUs with 32 kilobyte data cache and instruction cache. However, the issue here is that, right, none of the program can fully utilize the 6-way capability in your processor. As the previous table that I just showed you, most of the program can at most use 2.3 instructions per cycle. And even though you have simultaneous multi-threading, that doubles it to 4, right? So another idea they have is that, okay, if we don't build superscalar processor with that wide, what if I just build 2-issue processor? And the reason why they say 2-issue is because if you look at the table that we just show you, right, most of the time, right, this applications only use smaller than 1 or smaller than 2 or close to 2 instructions per cycle. So 2 is a reasonable choice in this way. So if we are aiming at just building a processor, we are just aiming at like building 2-issue processors within the same area, we can actually put 4 different processors in there. And if you look at if you look at the if you look at the amount of functional units we can provide on this 4 2-issue superscalar processor is actually giving you 1 more integer ALU, 1 more floating point ALU, and the same amount of cache, right? So it's a better deal in some sense, right? Because with 6-way superscalar processor, the best you can do is that, okay, I have simultaneous multi-threading, and if I have 3 integer ALU, it's reasonable for me to develop like a 3-way simultaneous multi-threading, so I can execute at most 3 programs at the same time. But if you have 4 different cores, you can actually schedule 4 different processes, 4 different threads, and because each program's ILP is smaller than 2 or equal to 2, so most of the time each process will not experience performance degradation. So that's why you see most of the processor right now, they have this architecture. So so this is the Intel Skylake processor, and this is on the die. So you are probably not so comfortable with this representation. So let me redraw the die in a different way. So this is a processor, and each processor would have a core. We have multiple processor cores, and within each core there will be registers, and there will be L1 cache, L2 cache that are private, and the last level cache, or say L3 cache, they are all shared. So this is the concept of chip multiprocessor. All right. So now we have roughly learned the concept of chip multiprocessor. And previously, we also learned the concept of simultaneous multi-threading processor. So I just want you to compare these 2 architecture. If I have the following scenario, which one do you think would be a better fit for the program, the workload that we are talking about in this question? All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so look at your answers. As I can see, wow, both A and V are pretty close. So it's definitely a case that we should go for a group discussion. So why don't we have you guys go into group right now? All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so now let's look at what you are discussing. So looks like, well, after discussion, 62% of you think it's A, 13% think it's B, 3% of you think it's I cannot decide which one. So now I'm going to invite a group to share your thoughts with us. Okay, Rocket Team. Showtime. Who is your scriber of the day? Raise your hand, raise your hand. Okay, if not, open to the public. Okay, I have Josh. Which team are you?
I'm on blue team.
Okay.
I really base this one on intuition, so I might be wrong, but I thought because the majority of the instructions.
What about your group? What does your group thought?
I don't know if people aren't feeling well, but nobody was very talkative in the group today.
Really?
So,
okay.
My intuition was saying because it's predominantly ALU instructions and it's able to exploit some thread level parallelism, P2 would actually be better because you'd be able to issue more of those ALU instructions.
Okay. So why P2 is able to issue more ALU instructions?
Because it has a wider issue pipeline.
It has a wider issue processor, right? And the key thing is that simultaneous multi-threading is essentially a wide issue superscalar processors shared by multiple processes, right? So they are all competing the same pipeline. So if you have a 4-issue pipeline, it means that both processes, they can freely use this 4-issue pipeline as long as they are able to get the amount of functional units they need. However, with chip multiprocessor, because they are physically isolated, and each processor can only run one process at a time without the help of simultaneous multi-threading. So in this way, each process can use at most 2 of the functional units, even though there are other functional units on the chip, right? Okay, yeah. So what else? Any other thoughts?
That was my major thought, was just that because it was mostly ALU instructions, having the wider issue pipeline would result in better performance.
Okay. So any other people have other thoughts? Any other people have other thoughts? Any other people have other thoughts? So quiet today because the weather is cold. Any other people? Okay, so what if, but one thing to think about is, right? The L1 cache is also shared among different processes, right? And as we said, the cache miss rate could be higher on SMT. On the other hand, although you said the 60% LU instructions, they can use 4-issue pipeline, but remember, Y also have similar instruction combination, right? So there's no guarantee that both of them would not compete this, or the X will dominate the execution, but if X has pretty bad data, and Y may be, may not be able to get a resource it wants. And the other thing is that, right, even though, so there are a lot of things to think about, right? So there's no guarantee that SMT will get better performance in this way. But on the other hand, CMP, because it has isolated resource, so it will at least give you comparable performance for well, I would say like guaranteed performance for both programs, right? So I was hoping to have more discussion on this question because this question actually has no standard answer. And I was trying to use this question to show you what I would like to see in your final exam, because in final exam, you are going to see a lot of this kind of open-ended question. And this kind of open-ended question, they don't have a standard answer. And what I would like to see is that, okay, saying it's like a GRE argument. If you argue for SNT, it has better performance. You also need to tell me why CMP doesn't give you better performance. So it's a little bit unfortunate that I didn't hear a lot of you talking about your thoughts about this question. But my feedback on this question is that, first of all, there's no standard answer for this question. The right answer is that it depends. So the only one who get it right is actually the one who chose C. Because there is no standard answer for this one. But you also need to give me why there's no standard answer for this one. Because for this question, there's no guarantee this 60% LU would be able to fully utilize the 4 issue or the 2 issue. What if both of them are linked list instructions, right? And here we are giving you the instruction combination, but without giving you the information about instruction count. So, does the parallelism created by the program affect the question? Yes, but so that's one of the potential that you can argue with. So a lot of things that you can talk about, and I would like to have you. So it would be nice that you can express your thoughts for to the rest of the class later on if we see this kind of question. But the truth of this question is that there is no standard answer for this one. All right, and think through all what you have read, and because there's no significant advantage of chip multiprocessor or simultaneous multi-threading. So that's why you are seeing that most of the modern processor right now, they combine these two together to exploit both threadable parallelism, but in the meantime, use the chip multiprocessor to isolate the resource to guarantee a certain amount of performance. And also there will be benefit in power consumption, which we will talk about in the next lecture, which tells you why we are seeking for chip multiprocessor design. But now let's accept the fact that most of the processor right now is a chip multiprocessor with simultaneous multi-threading, and it's more important that how we can use this processor for parallel programming. So if you have learned the operating system class, if you haven't, it's definitely a good time for you to consider enroll in CS202 next quarter. And parallel programming is very important, as you learned from the opening video in the first part of the class, right? The future is parallelism. Single cores are not getting any faster. That's what mentioned by David Patterson. So to exploit the parallelism, you need to break your computation into multiple processes or multiple threads. So in modern operating system, we provide these 2 different abstractions. The first is called processes. It's essentially considered as separate programs and running on your computer at the same time. And each process will have its own virtual memory space, meaning they have a different page table, and you need to explicitly exchange data, use inter-processor communication APIs, or use files or whatever mechanism that the operating system provides. And another abstraction modern operating system will provide, which is the main paradigm that we are going to discuss later in the lecture, is called threads. So the threads is considered as an independent portion of your program can run in parallel. So we are partitioning the computation only, but the virtual memory space, meaning that we still allow all threads to share the same virtual memory address space. So what does that mean is that in a thread model, only computations are partitioned, but the memory is shared. So that's the parallel programming that we are mainly talking about. And if you look at what software thinks about multi-threaded or multi-programming hardware, there is actually a huge deviation from the real architecture is. So so there are things that all of us agree. So from the hardware people and software people, we all agree that, okay, chip multiprocessor looks like this. We have core, we have registers. And what we don't agree is the memory part. So the operating system or all the programming paradigm, including those processes based programming paradigm, they all think the memory is shared like this. But as you learn from our, so when they designed the multi-threaded programming model, they use this shared memory to host the shared virtual address space and map the thread to each different processor cores. However, the truth is that in addition to this, in the hardware, as you learn, there will be L1 cache, L2 cache. Each are private to each processor. So what will happen is that if I have a code like this, saying that I have a loop and I have loop working on different parts of the array. And now, if I have a variable and I want to use different parts of computation to update a sum, the result of sum. So initially, I declare a variable sum equal to 0 in my shared virtual memory address space. And thread 1 got it. So I have a cache version of sum equal to 0. Another thread also have sum equal to 0. And in fact, everyone in a array have sum equal to 0. But as you could imagine, later on when we execute a program, thread 1 may like to update the sum value as something, right? But because it's privately in a cache, others cannot see the updated value without appropriate architectural support if the programming model looks like this. So again, software people, software programmers create issues and architects help them to solve the issue. So here it comes two kinds of architectural support to better support the correctness and the efficiency of parallel programming. So the first type of support we provide is called coherency protocol. So the coherency protocol in chip multiprocessor or say multiprocessor system, it guarantees that if all processors try to retrieve a value from a memory address at the same time, they should see the same value. They should see the same value. That's coherence. And consistency, it means that if we want to update a variable or a memory address, we all agree here is the order how we should update the variable. So coherency is about what value should be seen. And consistency is about what order should we perform those memory operations. So there are two types of architectural support that we support in chip multiprocessors. So let's talk about coherency first. So a very simple coherency protocol that we taught you in the textbook is called Snooping Protocol. So the basic idea of Snooping Protocol is that each processor would broadcast its cache message to other processors that are connecting to the same snooping bus. And for each cache block, we would have 3 different states. So previously, without chip multiprocessor, each cache block only has valid and invalid state. But now we further divide the valid state into 2 different cases. One is called shared, meaning that the data is valid for you to read. However, there are also processors might have the data and others might be able to read the data. So you cannot write it or update it. And if you want to update it, you have to make sure that the cache block is in an exclusive state, meaning that you have full permission on the data. So that's the simple cache coherency protocol. So if you think about this protocol, what it works out is that all the caches are connected to a snooping bus, and the valid bit will be extended as the state bit. And this state bit would contain 3 to 4 different states, and this different states indicating what the processor can do with each cache line. So the basic idea of snooping protocol is that in the very beginning, the data is invalidated. And if there is a read miss, meaning that I'm going to fetch the data for a read, so I will be going to the share state. But in the meantime, because I'm just reading it, it doesn't disallow other people to read it as well. So if you keep reading it, it will the cache line will be in the share state. And it only changes to exclusive state when you have a write request. And when you are trying to write, you will also have to broadcast a write miss message to that other people who have the share state to degrade their share state to invalid, because it means that some other core in a processor is going to update the cache block. So the cache block that you are obtaining is by no means it's going to be valid in the future. So you should change it to invalid. So here is the case, as you can see right now, other processor can also invalidate your cache copy. And when you are in exclusive state, you can do whatever you want. You can keep, if you are writing it, it will still be inclusive state. And however, when you receive a read miss from other processor, it means that other people is requesting the data. So you have to write back the data to the memory so other processor can fetch it. But in the meantime, it also tells you that other people might be able to use it. So you have to change it to share state. And if you hear some people is going to write the data, meaning that the current block needs to be updated. So you will write back your current data. So other people will get the up-to-date data to write. But in the meantime, part of your cache line will not be able to use. So just change it to invalidate. So that's the basic idea of snooping protocol. So with snooping protocol, what will happen here is that although initially we got a sum equal to 0 for everyone, however, if the processor one wants to update the sum, and it will broadcast the write miss message to everyone. So everyone's sum will be in invalidate states, which I put the color to be gray here. And then I can safely update the sum value, and I use the purple here, which is coherent to the previous slide, that the purple state meaning the exclusive state. So after I update this value, I'm the only one who exclusively have the right up-to-date data. So when somebody else saying that the third thread wants to update the summation value, it will has a read mask. It needs the value. It will broadcast a read mask, and then the exclusive state has to write back the value to the shared memory, and then both of them can now enjoy the value. So that's the cache coherency protocol. So to give you a better idea about coherency protocol, I am inviting you to think about what's the right answer for this question. Okay, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so now let's look at what you guys think. So it looks like most popular answer is C, but you never know if the two that you think is what other people would think. So let's have a group discussion real quick and let me know what you guys think after the discussion. All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so now seeing the answer after discussion looks like, oh, more of you think it's D. Okay, so what makes that change? That's one of the fun part of group discussion. Okay, instinct, what do you guys think? Somebody there? Somebody home? Raise your hand. Okay, if not, open to the public. Okay, I have Joshua.
Hey, Professor.
What does your team think?
So we discussed it and we thought that 3 of them were possible.
Okay, what are the 3?
We thought all of them except the second one.
Okay, why not the second one?
Because we're guaranteed that rights will be in order, and the second one has rights that would be out of order.
Where is the guarantee that the rights will be in order?
I guess we assumed consistency along with the coherency, but if we can't assume consistency, then
well, so it's not about a consistency,
that.
Right? So if you look at the order of thread in updating the variable, right? Sorry, not thread 1, thread 2 in updating the variable, right? Is monotonically increasing, right? So there is no way that you can go back to the future.
Yeah, those writes would have to occur in order.
Right. So that's why 2 is not correct. But under what situation are you going to see 1, 2, 1, 3, 4?
So 1 is like the obvious case where it bounces back and forth and keeps updating and then printing and updating and printing. 3 and 4, you could thread 1 could print 1 a bunch of times before control is given back to thread 2. And then thread 2 could do a bunch of increments and then bump back to thread 1, print 64, back to thread 2, a bunch more increments, and then back to thread 1 to print.
Okay, so seeing is believing, right? So let's just run the case, right? So here is the program that I show you. I have a different thread called modify loop, and a loop is going through 1 through 1,000 because my processor is really quick. So in the meantime, I have another thread keep printing the value, right? So now let me compile the program and let's run it. Okay, so for the first time, this is what I see. I see a lot of 1s and 185, 859, 1,000, right? Now let me run a second time. 1, some value in the middle, 1,000, right? Now keep running, right? Oh, I have a lot of 1s and I have 1,000, right? Which is coherent to the last case that I show you, right? So ironically, the case that we set makes most of the sense, right? Like so first of all, through the demo, right? We know that, well, at least okay, through the demo, at least we know that we see the third and the fourth case, right? In the first case, if you have a really slow processor, it would occur, but it rarely happens nowadays. But although it makes more sense, but it's actually the case that is also rarely happen today. So most of the time you are going to see either 3 or 4, but not the first one. Although if you have a really slow processor, saying that you have a processor that's about like 1 megahertz, you might see it. Okay, Winston, what do you think?
I just had a question. So is it the reason why the case 1 doesn't happen a lot? Like you said, it's because it's slow. Is it because it does it the newer, like higher, the more performant processors
Well,
want
so
to
if
stay in
you
the
take
same
operating
thread?
system, you should also, well, so there are quite a few things, right? So first of all, because your processor, another thing to think about is that the threads and the processes, they are scheduled by your operating system, and there is no guarantee that the operating system would schedule your process interleavingly. And even though we put them in the same simultaneous multi-threading processor or different processor cores, the cache coherency protocol does not guarantee that I will update the value of 0 right after, or say like, okay, so although this line of code may not be always executed right after I perform an update, because there's no guarantee that this will happen. So you cannot think that 2 will be executed interleavingly. So that's the main thing. I hope that's a good answer for you, Winston. Winston, are you okay with that?
Yeah, I think that makes sense. Yeah, because it's in the cycle. It stays in thread 1 for the cycle, like the whole allotted CPU
Yeah,
schedule.
so because you guys would think that those threads, they should execute interleavingly, right? But think about the scheduling and even think about the simultaneous multi-threading, right? We only schedule one of the other thread when we have free bandwidth. So it's not reasonable to think it will happen. So in fact, 3 and 4, they are the most popular one. And 1 rarely happens unless you have a really slow processor, really fair scheduler. However, what would never happen is the case of 2. So I would say 3 is the right answer, right? So now you start to feel like, okay, multi-threaded programming is not the beast that I'm thinking, right? And another thing to think about for cache coherency, that for each cache line, we have multiple variables within the same block. And now, if I have a thread 1 that I try to update a value saying that if I want to update 80. So it turns out that because the coherency protocol is operating on the block granularity. So even though I'm only updating 0, I still have to change the whole block as exclusive state, and other people's block will be invalidated. So if now thread 2 want to update A2, even though I'm not using the same variable as U2, but it will become invalidated again, even though originally I may have the block. So I have to invalidate other people's copy again to only retrieve the block to update the value that I want. So in this way, there's other cases called coherence misses in your cache. So now I want you to look at these two pieces of a code to tell me who would have better performance. Okay, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so now look at your answer. B is the most popular, and also more than half of you think it's B. So I will skip the group discussion here, but I need a volunteer to tell me why do you think B is the right answer? Okay, I have Jonathan. So which group are you? Malers?
Team Rocket.
Okay, Team Rocket. Okay. You tell me what do you think?
I think it's version R and B because the way it indexes through the data, it gives each thread a nice coherent block of data to work with, so they won't cache miss per thread.
Right. So if you look at the version R, right, and if you look at how they traverse the memory, so let's look at the version L. It's interleaving, right? So for the C array, it's more like, yeah, I'm going to update one by one. So so if I have two threads, right, thread 1 will work on this, thread 2 will work on this, thread 3 so it's very likely these are the same cache block, right? And for version R, it's better because thread 1 is working on this part, thread 2 is working on this part. So you can assume that the coherence miss is smaller, right? So that's a very, very good answer. So now I'm also going to show you a demo to tell you how significant is that. So here I have the matrix add, which is identical to the program that I gave you here. And I have the, is that matrix add p3.c? Okay, so probably the empty version. Okay, so I have a matrix add code, and this is identical to the code that I just showed you, right? So now what I'm going to do is that I am going to execute these two pieces of a code, And let's see how much time it takes to execute each of them. So the first version is actually the left-hand side. So for the left-hand side, let me see if I have this many, and is this, oh, oops, what's the second argument? Okay. Okay, so let me see if I have 4 threads. Okay, it takes this amount of time. And if I am running through, okay, am I doing it wrong? Wait. Let me check my makefile. See my makefile. Okay. So SSE 2 threads. Okay, so actually I think I should do the SSE demo. 2 threads. And okay, if I have 2 threads, it's too short. All right. Wait. Am I really getting it right? For the chunk version, maddmt.c, if I have, for the chunk one, yeah, I did that, right? For the chunk one. Wait, I don't think I recompile it. Okay, let me maddmt. Oh, you know what? Okay, let me recompile it and see what's going on there. So if I have the maddmt, if I make it large enough, so this one would take this amount of time. And if I have a chunk version, well, still slower. Okay, I will check that later. But supposedly the right-hand side version should be faster. Okay, so let me see what's going on in the demo. All right, so, okay, but the purpose of this demo is that I want to tell you that there is going to be another kind of miss, called coherence miss in your code that you have to be paying attention to, right? So a block can be invalidated because of the sharing among processors. In this case, it's called false sharing, that a processor will modify a memory address X, and processor may also want to modify a memory access Y, but because Y is invalidated because X, Y are in the same block. So for the performance for this case, the answer would be R, because the R version should have better separation on the code. Oh, I got a reason why my demo doesn't work out, because I have a simultaneous multi-threading processor. And if you have a simultaneous multi-processor, then it's highly possible that they are sharing the same cache. So it won't show you the difference. All right. So now, again, another demo that I wanted to think through. So consider the given code. You can, how many of the following values would you be able to see? All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so now look at what do you guys think. It looks like we definitely need some kind of discussion. So go ahead in a group discussion. Ten seconds. 5, 4, 3, 2, 1. Time is up. Okay, so now after discussion, I saw, wow, D becomes the most popular answer. So I want to invite a group to share your thoughts with us. Okay, Instinct. Who is the scriber of A? Okay, if not, open to the public. Which team would like to share your thoughts? Okay, I have Tyler Woods. Which team are you representing?
A rocket.
Okay, what do you think?
So it can't be the first one because A or B has to be set before X or Y could be set before it. We were between before any of those are set, like what are the default values? So we're just kind of assuming that there's 0. So both.
So you said it can't be the first one because?
A or B has to be set to 1 before X or Y could be set.
But you are assuming the case that, okay.
Well,
okay,
they can't
keep
go
going.
out of order. So it'd
Are
have
you
to be.
sure?
then it would be technically wrong. It would just be like
Okay,
incorrect speculative execution.
are you sure?
Fairly sure.
Okay, other thoughts? Other people, other thoughts? Okay, so keep going. So you said 0, 0 is not possible.
Yeah, and 2 and 3 would have to be either modify A or modify B, ending first to set those values, and then the other one not be 0 before the other one started. So, and then if both of them interleave, that would be the fourth output.
Okay, so do you want to stay a little bit and let me show you the demo? So now I have a program exactly the same. Agree with that? Tyler,
Yes.
is that the same program? Okay,
Yes.
so let me run this program. So so this is the program called fence. And I'm going to run this program for a little bit more times because we want to see all the values that are possible. So I have a file called output, and okay, and then I'm running it right now for several times, actually a lot of times. And let's see what the output looks like. So I do have a file called output now. As you can see, wow, after join, I have a lot of zeros, 1, right? But am I going to have 0, 0? Wait. Okay, wait. Oops. How come the demo today is not really good for me? Yes. Oh, wait. Okay, so you start to see there are some different values in there, right? Okay, so let's see what are those values are. Do we have a value like 0, 1 is here, right? Do we have a value like 1, 1? It's right here. Do we have a value of 1, 0? It's also here, right? Are we going to see the value of 0, 0? So it's not found here, but let me try to run it for a few more times. Maybe that will be different. All right, let's keep running it. Let's keep running it. Let's keep running it. All right, so if I run this for long enough, am I going to see a different value like 0, 0? Still no? Okay, so that's probably, I'm not in a good luck today. So let me change a computer and see how would that work. So this is still another program that I have, the same program that I have. And I have the multiprocessor, and I have the, oh wait, am I getting the right compilation flag? Oops. mfence.c mfence. Okay, so let me compile this. Oops. Just make fence. Okay, and let me go to tcsh, csh. Okay, and let me run this program for a little bit, and let's do fence, and let me do this output, ext. Okay, so let's keep running it. keep running it, keep running it, keep running it, keep running it. And let's see, what are the values we have? So see, here we have a 0, 0 here, right? Just in the seventh row, right? So from demos on different, on this processor, you will see that actually all the scenarios are possible, right? So 1, 1 is the most intuitive one that you guys might think, because thread 1 and 2, they might execute your instructions like this. And 0 and 1 is also possible if one thread is running ahead and the other one running behind. And 1, 0 is also possible. But how come 0, 0 is possible, right? Think about this. We have the out order execution hardware. And the out order execution hardware is scheduling your instruction based on the data dependency. Is there data dependency on these 2 lines of code? The answer is no. So there is nothing saying that your processor cannot reschedule these 2 lines of code. And turns out that you are going to see a scenario code 0, 0 because of out order scheduling. All right, so that's why all the 4 values are possible in this scenario, because you have out order scheduling. So now one thing you should learn is that multi-threaded programming is really hard because we have a lot of things to consider in our microarchitecture. So I will start with the explanation of this again in the next lecture. But before you leave the classroom, several things, a lot of due days, last project, last reading quiz, last assignment, and IEval, please do it. And it will give you a full credit assignment. And a good news for you is that if you are still struggling with your reading quiz, next Monday, I invited my friend Ritu Das from UMich to give a talk in ECE seminar series. Attend and submit a screenshot. It counts as a full credit reading quiz. And the final exam is any consecutive 3 hours you pick between this time frame, similar to midterm and about 1.5 times longer. And look at the definition of speed up. You should know how many questions are there going to be for 1.5 times longer. And 2 of the questions will be comprehensive exam questions. And we will release a sample final at the end of the last lecture. If you have questions, please use my office hour. Other than that, enjoy the rest of the day.